Hello everyone, welcome back to another video. In this video, we're going to take a look at a loaded beam from start to finish. We'll calculate the support reactions, construct the polar polygon, develop a funicular link polygon, as well as use them to produce an accurate bending moment diagram, not by guessing, not by memorizing shapes, but by understanding the force systems behind it. As you can see here, we have a free body diagram of a beam with its support RL to our left here and RR to our right here. We have three different loads or forces acting downwards: 100, 200 and 300. We have dimensioned the spacing between the loads. That shows the relationship between the loads and the beam and the different reaction points or the support points. And we're going to be using all these information to create our bending moment diagram, graphically that is. So let's get further into things. Now, before we get started, it is very important that you understand that when you are producing these drawings, that you're drawing based on a set scale. You'll determine this scale whenever you're doing yours. Alright? As you can see here to my left, I have a scale. So I'm saying here on my scale, for every 1 meter in measurement, it is equal to 1 centimeter on my paper. In this case, it is in AutoCAD. When this is printed, it will be the same 1 centimeter. Likewise, I'm going to be saying that the scale that I'm going to be using for a load is going to be equal to, for every 100 unit, is going to be equal to 2 centimeter on my load line. What is that? You'll find out shortly. So since we have this out of the way, let's get into things. So as you can see, I've already drawn my free body diagram here, and this one here is already to scale of 1 meter being equal to 1 centimeter. So here I have this here, from here to here is actually 6 centimeter, but in reality that actually 6 meter in real life, but on my paper it is in centimeter. So the first thing that we're going to do here is that, and that is after drawing our free body diagram, is that we're going to draw something or create our funicular or our polar link polygon. In order to do this, we must first extrapolate our load values and create a load line. Now, what is this load line? Our load line is going to be somewhere here to our right, but it could be to the left. It's up to you. What I'm going to be doing is that I'm going to represent these values here, these three values, as a line. Alright? And these values will determine how large or how long or how lengthy those lines are. For example, I say for every 100 units, it's going to be equal to 2 centimeter. So the first thing I'm going to do is that I'm going to draw a vertical line to the side here, going down. That is going to be equal to, using my scale, 100 units here is going to be equal to what? 2 centimeters. So I'm going to enter 2 right there, and now I have a line that is 2 centimeter right there. So let me change the color of that so you can see. I'm going to go ahead and draw another line exactly from here, continuing down, and this one is going to be equal to, so again, 100 unit is equal to 2 centimeters. So this one here will be equal to 4. So now representing that 200 being 4 centimeter. Alright, I can go ahead and change that color as well if I want, so you can differentiate. Then I'm going to do my final line that is going to represent this 300 force here, and that one there will be equal to, for every 100 it's equal to 2, so that is going to be equal to 6 centimeter. Alright, let me change the color of this as well, and I'm going to make it blue. Okay. Alright, so this here, this line here that I have here, this is your load line. So this is your load line. Alright, let me see if I can add some text here. This video might be a bit lengthy. Alright, so let me just turn off this here, and then I'm going to write the information there so you can see. So this is your load line. Alright, so this is your load line. Let me rotate this, RO. So this is our load line. Alright, so this here is our load line, and it represents the values that we have there. Alright, now next thing that we're going to do is that we're going to label these points here. Now remember, these lines here represent the loads, and we have our bows notation here already between the different forces, so we're going to be representing that here. Alright, so with this line here being this 100 here, it means that this line here will be between point A and B. Alright, so we're going to add that text there first. Let me just go ahead and copy this one here, and then I can always edit it afterwards. So let me go ahead and add my text right here. So I'm just going to go ahead and just place some letters. So this here will be A, and this in this instance is going to be common letter, a common letter. Alright, so let me just copy it down to the other locations. So one is going to be here, here, and then at the bottom down here. Now remember, we're labeling them. So this 100 line here, this is the 100 line, is between bows notation A and B. So it means that this is going to be A here, this one here is going to be B. So let me write B right there. Then we have this load line here that is representing the 200, and it is in between B and C. So with this being B, it means that here is going to be C. And I'm sure you get the drift. So it means that the next point down at the bottom there is going to be what? C and D. So it's going to be what? D. Alright, excellent. Alright, so now that we have that in place, the next step is that we're going to identify a point that we're going to call our pole. Alright, now what is that going to be? And let me go ahead and I'm going to write something over here, and I'm going to add a point somewhere here. Alright, PT, enter. Alright, let me change it to a different style, and then go ahead right there. So this point that you're seeing there, that point there will be called my pole. Alright, now if you're wondering what's the dimensions for this, now this point here, which is point O, which is the pole, that point there, believe it or not, is random. You decide. Personally, for me, I always like to put it somewhere in the middle for some reason, and that's just a preference of mine. However, that point there, or this pole here, is random. It is random. Alright, so this here is our pole. Alright, so that's our pole. Alright, that's this cross here. Now what I'm going to do from here, or the next step, is that you're going to be drawing diagonal line from your load line to your pole. Alright, so for example, from A to the pole and then back to B. Now if you're unable to snap to your pole, just ensure that node is turned on your AutoCAD. That is if you're using AutoCAD to produce a drawing like this. Alright, now the next step is to continue the process. So now I'm moving from C, and I'm being careful to ensure that I'm snapping to the right thing, to our pole, and then back to the end there. Alright, excellent. Now once that is out of the way, alright, the next thing that I'm going to be doing is that I'm going to be labeling this here, because I'm labeling it as I'm going along, because this is a teachable moment for you, and this is what you're going to, well, this is what you'll have to do in your exam, on your exam in May, June. So this here is your polar, alright, this is your polar polygon. Alright, so that's your polar polygon right there. This entire thing here is your polar polygon. Let me scale this down a bit. 0.4. Alright, so our load line, scale down a bit, or labeling, scale down a bit. Alright, now once we have that in place, it's now time to turn our attention to creating our funicular link polygon, and that is extrapolating it, if you want to call it that, from our free body beam diagram here. Now how do we do this? What I want you to do is that you're going to be projecting lines down from every point where there is some force acting on the beam. So once there is a force acting, then you're going to project a line down. So for example, from here, which is R L, you're going to have a line projected down as well there, and every other point where there is a force acting. So for example, here where the 100 is acting, that's a point. Where the 200 is acting, that's a point as well. Here where the 300 is, that's a point as well, because all of those are force acting. RR here is another force acting as well. Alright, now if you have watched any of my other video, you'll understand that when I speak about loads and I mention something about them cancelling each other out, and we'll touch on that further on in the lesson. Alright, so we have the forces here, and we have this force acting up, this force is acting up. So we have these two forces acting up, but we have three forces here acting down. So it means that in order for this beam structure here to survive or not collapse, it means that whatever is acting down, the minimum force acting up has to be the same thing or even more, if you want to think about it like that, in order for it to cancel out each other and everything to be safe. So let's continue. So we're now trying to create our funicular link polygon. Now, how are we going to be doing this? We're going to do this by simply taking these lines that we have here, these lines here, all right, all these lines here, and we're going to be moving them over to our funicular link polygon area where our beam is here. So I'm going to start things off first by identifying a point. I'm just drawing a random line here. Now this is a reference line for me. Now here's what you're going to do to determine it. So in order for you to do this now is that you're going to take this line here, that's the first line at A there that runs to the pole, and you're going to copy it. Now the reason why we copy it is because we want it to be parallel to what we're going to be doing over here, because we could have always find the angle of this here between here and then manually draw it here, but we're not going to be doing that because we're using sophisticated software. So when we copy things, we're literally creating a replica of it. Now once you have drawn the line, right, the next thing that you're going to be doing is that you're going to ensure that it touches the force that it's actually representing. All right, so from here you'll realize that it doesn't go all the way over to this line here, so it means that we're going to extend the line so that it touches this one here. All right, so we're extending it so that it touches it. All right, now the next thing we're going to do is that we're going to take the next line that is coming right here. All right, so this line here, all right, because all of these are coming from your 100 meter. So we're literally just working our way down the line. So this is the next line you're going to copy. Once you copy it, select your base point, and then you're going to place it at the, should I say, the head of this one here. So remember the head and tail situation that we mentioned. All right, now again, it's not touching this line here, so it means that we're going to extend it over to touch it. Likewise, if it had stretched beyond the point, then you know you'll have to trim away the excess so that it touches this line here. So now we're at this point here, so we're going to now copy this line here. All right, and we're going to place it where? Right there. All right, now it needs to touch this line here. I'm not sure if I extend this it will touch it, but let's try. All right, perfect, almost there. Now we're at this point here, so we're going to grab onto this line here, and I'm going to copy it, and I'm going to place it where? Right here. All right, now you'll notice in this instance the line has passed or surpassed this line here running down at RR, or running down from RR. So what are we going to do? We're going to trim away the excess. All right, so this line here is representing, I'm going to make it green. All right, we have this line here, I'm going to make it orange, so you see where it is coming from, and then we have the white line, and then let's make this line green as well. All right, excellent. All right, so once we have that in place, we're now almost there. All right, now once you have done that, let me just erase this line here that I have going across. you're now going to connect a line from this point here that I'm going to call point X CP. Alright, that's CP right there, to copy it right there, and this point here, point X. Alright, and then we have this point here, I'm going to call it point Y. Let me ensure that I'm not. Alright, point Y. Alright, so once we have point Y there, and you realize that they literally fall in line with everything that is on this side here for some reason. So you see, things always work out the way it should, despite everything being random. It falls where it should. So you realize that this lines up with this perfectly, and this lines up with this perfectly, despite of all that we have done a while ago. Alright, now once that has been done, we're going to connect point X with point Y. So let me go ahead and do that now, and draw a line to connect both of them. Alright, now technically this is what in previous video when we were looking at forces, this is basically your EQ line, your equilibrium line. Alright, so this would be your equilibrium line. Let me just change the line type scale of this here so it looks a bit more presentable. Let's go 0.4. Alright, a bit lower, 0.2. Alright, so that is it right there. So once you have created your EQ line, alright, you're going to grab onto this line here and you're going to copy it. So similar to how you copied these lines over to this, you're going to copy this line over to your pole right there. And again, it has passed or surpassed your load line, so we're going to trim away the excess that goes beyond your load line. So this is now your EQ line. This is now what? Your EQ line, or equilibrant line. Alright, so this is your equilibrant line right there. So we're going to go ahead and we're going to do some labeling now. So let me go ahead and copy this CP so you can see what is going on. So this here is your let's go. I'm going to write EO. This is your EO. Let me copy this as well. And you might be wondering, why is it called EO? Remember that this point here is O. You'll now know that this point here will now become E. Let me double tap on that there. Alright, so that is how it got its name. Alright, so EO, that's how that line came about. Likewise, all of these points here do have numbers and names as well. So for example, as you can see, this would be AO, BO, EO, CO, DO, so on and so forth. Alright, now what's the next step from here? Alright, because what we have here now, this is your should I say it? Alright, I'm going to write it for you. This here is your funicular, alright, funicular or link polygon. So this is now your funicular or your link polygon. Alright, let me turn this off so it doesn't snap to the wrong thing. Alright, so this here, that's this shape that we have here. This is your funicular link polygon. Alright, why is it a polygon? It's a polygon because it has what? 1, 2, 3, 4, 5 different sides. Alright, it might not be what you're accustomed to with a octagon or a pentagon or a hexagon, but yes, this is a polygon, believe it or not. Remember, even a triangle is a polygon. Alright, so let's continue with our process. Now the next thing that we're going to do is that we're going to be connecting this line here, which is your DO line, to your AO line. How are you going to be doing that? If you're using a software like AutoCAD, you can simply use your fillet tool and fillet your AO line with your DO line. Alright, you'll connect those together just like that. Alright, now once you have done so, the next thing that you're going to do is that you're going to be drawing a line, a vertical line, from where these two lines intersect, that is AO and DO, and you're going to draw a line all the way up, a perfect line until it touches your free body beam right there. All right, also something to note as well, where these two lines, all right, which are basically your DO, your BO line and your CO line intersect as well. Remember this line that we have here running up. All right, you realize that what is happening is that it forms a force, or a little zone, not a force but a zone within the space here. All right, it forms a little zone within the space. All right, but nonetheless, we have our EO line there. We're going to be copying this text here just because it is already vertical. All right, and I'm going to write the name of this line here as well. So this line here is also your, and I'm going to change the text, your equilibrant. So this is your, and if it's not equilibrant, let me double check on that. Equilibrant. All right, so this is your brand. All right, so let me up the, all right, I might have to scale this one up, scale, and make it twice the current size. All right, so this is your equilibrant line. All right, and I'm going to make it orange, well, yellow, so you can see what it's actually representing. All right, so as you can see here, this is your bending moment diagram that we have just created using graphical method. All right, now we can use these values now, or these positions now, to determine the reaction at R, L, and RR. How do we do this? We can simply measure from here, point A to EQ. All right, from point A to EQ, and this, let me put it on the right layer. All right, let me go to that layer there, and we measure from here to EQ as well. So from D to EQ, now from D to E, and from A to E. Now remember, we had used a scale now, so we can now determine how much of the load RR is carrying of the entire thing, and how much of the load RL is carrying of the entire thing, just by using our scale and the measurement that we got here. All right, so as you can see, this is what, 4 units. All right, and remember, we worked out something, right? 4 centimeter here. So remember, for every 2 centimeter, it is actually what, 100 units in real life. So in this case, if this is 4, it means that it is going to be equal to 200. So it means that, and this up here being RL is carrying about or approximately, because I think AutoCAD is scaling or rounding off my numbers, approximately 200 of that load on this side here. And then now the other remaining balance is being carried by RR here, as you can see. Now let's see if we can do our manual calculation to determine all of this here before we go. So let me just open up some text here, and we're going to be working out the calculation. I'll be showing you how we go about manually calculating the reactions of simple free body diagram of maybe a loaded beam or slab. Let's see if we can do this. Now, how do we do this? I'm going to start by saying moments, or the moments is simply basically the turning force. So moments all right, at where? RL. All right, so RL. All right, and this as a value. All right, so I'm just going to start there, and I'm going to be where. How do we calculate this now? What do? We start things off by first multiplying the distance the force is away from RL, and we're going to be doing this for all of them, and I'm going to be trying to simplify things as best as possible. So what do we know? We have a 100 force here, we have a 200, and we have a 300. So let me go ahead and write that down there. 100, 200, and a 300 force. All right, and all of those will be multiplied against the distance that they are away from RL. So how far away is 100 away from RL? That is 6. All right, so I'm going to enter what? 6. All right, then we know that how far away is 200 is how far away 200 is away from RL. So we're seeing 8 here, all right, and we're seeing 6 here, so it's a total of 8 plus 6. So if we add the two values together, we will get what? We'll get 14. So it is 14 meters away from RL. Now for the final one, how far away is the 300 away from RL? So we have 6, 8, and 6 all added together will give us 20. All right, so now let's see how much force these are pushing or based on how far they are away. So what are we going to do here? We're going to simply multiply 100 times 6, which will give us 600. And we are also going to multiply 200 times 14. That should give us, as my maths is not working, 2,800. I think that's correct. And then now we have the final one, which is 300 times 20, which is about 6,000. All right, 6,000. All right, so once we have those values, the next thing that we're going to do is that we're going to be totaling these values together. All right, we're going to be totaling these values together. And what is the total that we're going to be getting? So we have 600, all right, plus 2,800, all right, plus 6,000, all right, and this will give us a value of, I believe, 9,400. All right, 9,400. All right, so that's the total force. All right, that's the total force. All right. All right, so that is it there. All right, now we're not through. We now need to determine the moments at RR. All right, now because this is the total, so now how are we going to determine that? How do we determine that? Here's how we determine it. We're going to take, all right, the total distance that we have here, the total distance across the beam, which is 6 plus 8 plus 6 plus 4, and I believe that is actually 24. All right, so moments at RR. So I'm going to write that down now. Moments. All right, and this is RR. All right, moments at RR. All right, now let's do this. So we have 24. All right, so we have the 24, right? That's the moments, and we're going to be multiplying that. All right, so we have 24, and we're going to be taking that value across to, so we're going to say 24. All right, 24 multiply by R. All right, and that is going to be equal to 9,400. All right, let me see if I can predict up this here. All right, so Alright, so that's where that comes. So we have the total distance across multiplied by RR should give us 9,400. Now, here, in order to determine this, we're going to have to do some transposing. So we need to make RR the subject. So what are we going to be doing? We're going to be taking our 24 and we're going to be putting it over here. Since it is multiplying on this side, when it comes across, it's going to be dividing. In other words, depending on the type of maths person that you are, you might say you're dividing each side by 24. So if you go over here and you divide over this side by 24 and divide this side by 24, the 24 will cancel out that 24, which will be equal to 0, which will leave us with just R. Alright, and then we'll on this side here we'll have the 9,400 divided by 24. Alright, so we have the RR divided by 9 there, and RR will now be equal to RR will now be equal to 9,400 divided by 24. That should give us 391.66. Alright, so that will be it right there. Now, so it means that the force at R is going to be equal to, and let me see if I can probably paste it right here. So RR force will be equal to that. Let me scale that down to 0.6. Alright, so RR force is that right there. And now, how do we determine the force that RL is going to be carrying? What do? We have to first calculate the total forces that are acting down. Alright, because remember, downward force has to be equal to the upward force in order for it to survive. So if when we're calculating this here, we need to add all the forces. So what are the forces that we have? So we're going to say that RL is equal to, we're going to say that RL is equal to the forces, which is the 100 plus the 200 plus the 300, and I think I should have it here, so I'm going to write them down. So RL is equal to 100 plus 200 plus 300. Alright, and that is going to be equal to 600. Alright, now you see that 600, we're going to take that 600, and we're going to minus the value that we got where up here for RR. Alright, the value that we got for RR, and when we minus that value, we're going to get 208. Alright, 208.34. Alright, so we now know that RL as a value of, alright, so let me just escape from there and match this property there. Alright, right there. Cool. Alright, so right there. So here we have RL value. Alright, so of the total 600 force that is acting down, on the left hand side here, RL is carrying 208 out of it, and on the right side here, RR is carrying 391.66. So RR is carrying the bulk of the load that we have here, as would be expected, as you can see here. Alright, as you can see here, because remember because here I know that AutoCAD is rounding things off, but if we were to measure this, do we have a ruler tool here? Alright, it hopefully gives us a more accurate measurement. Let's see if we can measure distance from EQ to So it's still it's still rounding off my answers to that value there, but there we go. This is the value that you'll be getting if you were to do your conversions based on the distance that is here. So believe it or not, that is it. That is it. So this is how we graphically represent. This is how we graphically represent or graphically produce an bending moment diagram based on a given load diagram using funicular link polygon and the polar polygon. Alright, now if you found this video helpful, don't forget to go ahead, leave a like, share and subscribe. If you're in need of a tutor for your exam, feel free to reach out, and I'll see you in the next one.